Hi everyone, welcome back to my channel E-shikshana. Hope all are doing good. In this video, we'll discuss about logic gates. Let's start the video. The content of the video are the basics of logic gates and binary logic and the process of conversion of AND logic. Let us first understand binary logic and voltage levels. Signals in digital electronics have two distinct voltage levels, that is high or low. For example, a system may be defined 0 volt as logic 0 and 5 volt as logic 1 with the built-in tolerance for any variations in the voltage levels as shown in the diagram. The threshold for logic 0 may be 0 to 1 volt range. Any voltage between 0 to 1 volt is considered as logic 0. Similarly, for logic 1 may be 4 volts to 5 volt range, and any voltage between 4 to 5 volts is considered as logic 1. In digital logic, only two voltage levels or states are allowed, logic 1 and logic 0, or high and low, or true and false. Most of the digital systems uses positive logic, in which a voltage level 0 or low is represented by 0 volts or ground, and logic level 1 or high is represented by 5 volts. Next, we'll try to understand what are logic gates. Logic gates are simple circuits that takes one or more input signal and send out one or more output signal. These are the building blocks of the digital circuit or a digital system. The relationship between input and output is based on certain logic. The basic gates are AND or NOT, and universal gates are NAND and NOR. Apart from these gates, we have tri-state buffer, XOR gate and XNOR gate. The standard commercially available digital logic gates are in two basic forms, TTL and CMOS. TTL stands for transistor logic with 74XX series, and CMOS is a complementary metal oxide silicon with 4XXX series, both in integrated circuit forms or IC forms. We'll not go into details of the construction and IC labeling. Let's begin with AND gate. This is a symbol for AND gate. The AND gate takes two or more inputs and perform logical AND operation on them. The truth table is given here, in which both inputs to the AND gate are 1, the output will be 1, and any other combination with one of the input is logic 0, the output results to logic 0. Next, we'll discuss about OR gate. The symbol for OR gate is represented as shown in the figure. The OR gate takes two or more inputs and perform logical OR function on them. The truth table can be given as, wherein if one or more inputs are logic 1, then the output is logic 1, and if both inputs are logic 0, then the output is logic 0. Next, we'll discuss about NOT gate, and it is also called as inverter. The symbol for inverter is represented as shown in the diagram. The output value is opposite to the input, that is 0 input will produce logic 1 output and 1 input will produce logic 0 output. This is the function of the inverter. Next we'll discuss about tri-state buffer or simply buffer. The symbol for buffer is given as shown in the diagram. Buffer does not change any logic level but used to isolate or amplify the signal by the use of control signal. Next we'll discuss about NAND gate. A symbol for NAND gate is represented as shown in the diagram. The NAND gate functions like AND gate with an inverter at the output. The truth table can be given as it produces 0 output when all inputs are logic 1, and for all other set of inputs the output is logic 1. Next we'll discuss about NOR gate. The symbol for NOR gate is given as shown in the diagram. The NOR functions like OR gate with an inverter at the output. The truth table is given as it produces logic 1 output when all inputs are logic 1, and for other set of inputs the output is logic 0. NAND and NOR gates are used extensively in the digital design because they are easy and inexpensive to fabricate. These are also called as universal gates because AND, OR and NOT gates can be implemented using NAND and NOR gates. Next we'll discuss about XOR gate. The symbol for XOR gate is represented as shown in the diagram. The truth table is given as it produces logic 1 output when one of the input is logic 1, and if both inputs are the same it produces 0 output, or we can say if one of the input is logic 1 then the output follows that input. The symbol for XNOR gate is given as shown in the diagram. The truth table for XOR gate can be given as it produces 0 output when one of the input is 0, and if both inputs are same it produces logic 1 output, or we can say if one of the input is logic 0 then the output follows that input. Next we'll discuss about the conversion of AND OR to NAND-NOR logic. To convert AND OR logic circuit to universal gate, follow the below steps. The first step is to draw the logic circuit using basic logic gates. Second step, for NAND implementation, add bubbles on the outputs of the each AND gate and bubble on the input to the all OR gates. For NOR implementation, add bubbles on the output of each OR gate and bubbles on the input side to all AND gates. Each line that receives bubbles in step 2 or in step 3, replace the bubbled OR by NAND and inverter by AND, or input bubble AND by NOR and inverter by OR, and eliminate double inversion. So these steps are represented for conversion of NAND or NOR logic for both. Let's see the conversion of AND OR logic to NAND-NAND logic for a given expression y equal to AB plus BC plus AC. The first step is to draw the logic circuit using basic logic gates as shown in the diagram, where we have 3 AND gates and 2 OR gates. The second step is to add bubbles on the output of each AND gates and bubbles on the input side to all OR gates. By adding bubbles and the bubbles on the input side of each OR gates. The third step is that to add an inverter on each line that received bubble in step 2. Hence we have added a bubble on the output of each AND gate, hence representing a bubble. Hence we have added a bubble on the input side of OR gates, hence the inverter to be represented here as well. And this OR gate also receives a bubble at the input side, hence we have added an inverter to this line. The next step is to eliminate the double inversion and replace input bubbled OR by a NAND gate and inverter also to be replaced by an NAND gate. Hence these 3 lines have the double inversion and these 2 OR gates to be replaced by the NAND and the inverter also to be replaced by the NAND. Hence by replacing them by an NAND gate we can convert NAND-NAND logic. Next we'll discuss about implementation, and this is a circuit what we can represent for a given expression. Next step is to implement bubbles on output of each OR gate and bubbles on the input side to all AND gates. So here we have represented a bubbles too. Third step is to add an inverter on each line that receives a bubble. So hence this receives the bubble, we have represented the inverter, and this AND received a bubble which we have represented inverter, and a inverter here as well, and this AND received a bubble, hence we have represented this inverter, and also this line receives the bubble and we have represented inverter here. Next step is to eliminate the double inversion and replacing input bubble AND by NOR and inverter by NOR. Hence by eliminating these double inversions, these 2 AND gates represented by the NOR gates and these 2 inverters to be represented by NOR gates. Hence we have converted the NOR logic. You can try solving for the other examples by following these steps. This is it in this video. Thank you for watching. Let's meet in the next video. Till then, stay safe.